Hello APC Mechanics students in Unit 7 in Gravitation, Class 3 7.1 in Gravitational Forces Part 3. In today's video we're gonna solve some exercises on what we have explained so far. A ball is tossed straight up from the surface of a small spherical asteroid with no atmosphere. The ball rises to a height equal to the asteroid's radius and then falls straight down toward the surface of the asteroid. The acceleration of the ball at the top of its path is at its maximum value. Now we can directly eliminate potential answers that are wrong. No, it's not maximum, because as we go away from the asteroid, the gravitational acceleration will decrease. It's not zero. Okay, so it seems that we need to calculate G. Now G is given by Gm divided by r square. R is the radius of the asteroid. Now, if we rise to a height equal to the asteroid radius, so basically let me assume that this is the asteroid of radius r, and it rises here, then the distance r should be changed into the double, because this is also r. Now, so r doubles. Now we can apply the factor of change. That would be 1 divided by 2 to the power of 2, which is 1 over 4, which means D is the correct answer. It is equal to 1 over 4, the acceleration at the surface of the asteroid. Now again, exercise 2. A ball is tossed straight up from the surface of a small spherical asteroid with no atmosphere. The ball rises to a height equal to the asteroid's radius and then falls straight down toward the surface of the asteroid. What force, if any, act on the ball while it is on the way up? We know that we have the gravitational force. Then we can directly eliminate E and D, because indeed they're mentioning that we have both a constant gravitational force and a decreasing force. We don't have this force. Now this is okay. So here, if you look at the choices A, B, and C, they're talking how does the gravitational force vary. It is not constant, because R changes. On our way up, we know that the gravitational force decreases, making A to be the correct answer. Now, exercise 3, the elliptical orbit of a comet is shown above. Positions 1 and 2 are respectively the farthest and the nearest position to the Sun. And at position 1, the distance from the comet to the Sun is 10 times that at position 2. Now, this is, let me say that this is R1, and that's R2. Let me label them. So this is R2 and this is R1, because R1 is greater than R2. We have that R1 equals 10 of R2. We need to compare the ratios F1 over F2, in which F is the force due to gravity. What is the ratio F1 over F2 of the force on the comet at position 1 to the force on the comet at position 2? So here they are referring to the force exerted by the Sun on the comet. And as you can see that the path or the orbit is elliptical, as we shall see in the coming classes. It's not perfectly circular. However, we can always, in this case, apply the gravitational force. The thing is that we cannot use the relations that are given by V is the square root over Gm over R, or the period to be given by the square root of 4 pi R cubed divided by Gm. These cannot be used. However, we can always use that the force is given by Gm1 m2 over R square. Then F1 over F2 would be Gm m over R square. So this is 1 divided by G m over R2 square, in which represent the masses of the Sun and the comet. We can simplify these. We're left with 1 over R1 square and 1 over R2 square, and that would be equal to R2 square over R1 square. Now that would be R2 square divided by 10 R2 to the power of 2, which is 1 over 100 basically, because the radius simplify, which means F1 over F2 equals to 1 over 100, making A to be the correct answer. Now, a new planet has been discovered and given the name Planet X. The mass of Planet X is estimated to be 1/2 that of Earth, and the radius of Planet X is estimated to be twice the radius of Earth. So the mass is being halved, and the radius is being doubled. The acceleration due to gravity in the surface of planet X is gx. The acceleration due to gravity on the surface of Earth is ge, which means we need to apply the factor of change. We know that the gravitational acceleration is given by gm over r square. We have all the factors, so that would be 1 multiplied by half divided by 2 to the power of 2, which is basically 1 over 8, making A to be the correct answer. A satellite needs a speed v to maintain a circular orbit of altitude h is 1 over 4 rp, in which rp is the radius of the planet. Now, because we're talking about circular orbits, we're allowed to use v is given by the square root of gm over r, and remember, if this is a free response problem, we need to derive this from scratch. An identical satellite orbits the planet at an altitude of 2h. The speed of the second satellite is... So from the choices, it seems that we need to apply the factor of change, but here we need to determine the relation between the previous radius and the new radius, because we're talking about altitudes and it's not very straightforward. So let me draw two figures representing the two orbits. This is the first one, and that's the second one. So this is RP, and this is RP. Initially, we are at the height h. So here, the radius, which is the separation distance center to center, is given by RP plus 1 over 4 RP. That's basically 5 over 4 RP. And for the other satellite, which orbits at an altitude of 2h, then the separation distance r is given by rp plus 2h. H is given by 1 over 4 rp. Then that would be 1 plus half, which is 3 over 2 rp. Then the previous separation distance is given by 5 over 4 rp. And the new separation distance is given by 3 over 2 rp. Now, why this is important? Because if we do r2 over r1, that would be 3 over 2 rp divided by 5 over 4 rp, which is 3 over 2 times 4 over 5, and that would be 6 over 5. Then r2 changes by a factor of 6 over 5. And now we can say that the speed is given by the square root of gm divided by r. Now we can apply the factor of change. That would be the radical of 1 divided by 6 over 5, which is radical 5 over 6. Then the factor that we're searching for is c, which is radical 5 over 6. Here, notice carefully that we couldn't apply directly the factor of change. We need to know how does the new radius or the new separation distance is related to the previous one by calculating the ratios. Now, astronomers collect data for several moons in orbit around a distant planet. The data collected are the distances between the planet and each moon and the period of the circular. They mentioned that it's circular, then we can use the relation which is given by v is the square root of gm over r, and the period is given by the square root of 4 pi square r cubed divided by gm. Of each moon around the planet, the data are shown in the table. The data for moon A, so we restricted to A, are used to collect the mass of the distant planet. The mass of the planet is most nearly. For the first row, we have the distance and we have the period, and definitely we can determine the mass of the planet using the relation. The period is the square root of 4 pi square r cubed divided by gm, in which m is the central mass, which is basically the mass of the planet. Remember, if this is a free response, we need to derive it from scratch, but because it's an MCQ, if you know already the formula, you can directly use it because they don't care for your solution. We are interested in determining the mass m. Then squaring both sides, we have t square is 4 pi square r cubed divided by gm. Isolating for m, we get that m is given by 4 pi square r cubed divided by gt square. And now we have everything. So 4 pi square, the distance is given by 3.4 times 10 to the power 8. Now it's healthy also to remember the value of g, which is 6.67 times 10 to the power minus 11. If you forgot the value, it's provided on the first paper of your exam. Multiplied by the period, which is given by 8.3. You need to be careful to the units. The distance is given in meters, that's fine. The period is given in month. We know that every month is 30 days, and a day is 24 hours, and hours need to be converted to seconds. We should multiply by 3,600. Why 3,600? Because each hour is a 60 minute, and 60 minute times 60 seconds, that would be 3,600 seconds, which is basically 30 multiplied by 24 multiplied by 3,600. Okay, raised to the power of 2. Plugging that fraction on the calculator, we would get mass given by 5.03 times 10 to the power 22 kg, which makes C to be the correct answer. Notice that A and C are close at the first glance, but the orders of magnitude are different. This is 10 to the power 11, this is 10 to the power 22. Again, the acceleration due to gravity at the Earth's surface is g. Astronauts are traveling to another planet that has 3 times the radius, then the radius would change by a factor of 3, and 4 times the mass of Earth, then the mass would change by a factor of 4. We're interested in the acceleration, which is g, then gm over r squared. Now we can apply the factor of change. That would be 4 divided by 3 to the power of 2, which is basically 4 over 9, making A to be the correct answer. Now, the mass and the radius of Earth are me and re respectively. The mass and the radius of the moon are given by the following factors, which means that we can apply the factor of change. The acceleration due to gravity on the surface of Earth is g. The acceleration due to gravity on the surface of the moon is most nearly. We know that so we can directly eliminate potential answers. We can eliminate C, D, and E because we know that g on moon is less than that of Earth. It's not 0, making B to be the correct answer. And you should always remember that g on Earth is equal to 1 over 6 g on moon. Okay, even if you forget all of this information, we can derive it, which is given by g is gm over r squared. Now we can apply the factor of change. That would be 1 over 86 over 2 over 7 to the power of 2. That would give us almost 0.14. And you can check that the closest to this one is 1 over 6. Okay. Now, identical satellites x and y of mass m are in circular orbits. The moment they mention circular orbits, we can use the relations that we have talked about, given by v's square root gm over r, and the period, which is given by the square root of 4 pi square r cubed divided by gm. And if it is a free response problem, we need to derive them from scratch. The radius of the planet is r. Satellite X has an orbital radius of 3r, so luckily they didn't provide the altitude, they provide directly the separation distance. And for y, it is given by 4r. The kinetic energy of the satellite X is kx. The kinetic energy of the satellite y is ky, so this is a repeated statement. Let me eliminate it. We need to find the ratios kx over ky. We can directly eliminate potential answers by trying to understand what's happening. If we are closer to the center of the planet, it means that our kinetic energy is greater because the speed is greater. So kx is basically greater than ky, then the ratio kx over ky is a number which is greater than 1. Then we can directly eliminate A, B, and C. We're left with D or E. Now let's determine the kinetic energy for each. So kx over ky is basically half mv square x over half mv square y. We can eliminate these, in which m represents the mass of the satellite, which is here. Now that would be v square x over v square y. Now because we are in a circular orbit, the speed is given by the square root of gm over rx to the power of 2. That would be the square root of gmry to the power of 2. We can cancel the square roots. M is the central mass, which is the same for both. We can eliminate these. That would be ry over rx, because we have 1 over rx over 1 over ry. Now ry is 4r, and that would be 3r, which means it's 4 over 3. And indeed, D is the correct answer. Now, identical satellites X and Y of mass m are in circular orbits around a planet of central mass. So we have the same given again. The radius of the planet is r. Satellite X has an orbital radius of 3r. Satellite Y has an orbital radius of 4r. The kinetic energy of X is kx. Satellite X is moved to the same orbit as satellite Y by force doing work on the satellite. In terms of kx, the work done on satellite X by the force is. So what's happening here is that the satellite which is found in the orbit X has been moved to Y. And this doesn't happen only if we perform work, which means that energy has been extracted or injected to the system. So in order to determine the work done on the satellite X by the force in relation with the kinetic energy, which means we need to use the work energy theorem, and this is a very important exercise. So let's apply the work energy theorem. The work energy theorem states that the variation in the kinetic energy is equal to the work done by the external forces. Now, what does delta K represent? Delta K represents the variation in the kinetic energy between final and initial. So, which is delta K, that is K final minus K initial. Initially, we were at the orbit X, and finally we are at the orbit Y, so this is ky minus kx. So let me state here, this is ky minus kx equals. Now, what are all the external forces that are acting on the satellite X when X moves from the orbit X to the orbit Y? Now, first of all, we have the work done by the force that we are interested in calculating. So let me say W. Okay, plus. Now, this is not the only force. There is another force doing work on the satellite X, which is the pull of gravity. So we need to say also we have another force, which is WG, and we're interested in determining W. Now, because our answers are being expressed in terms of kx, we need to change ky to be kx and wg to be kx as well. From the previous exercise, we know that kx over ky is equal to 4 over 3. So if you cross multiply, this means that ky is 3 over 4 kx. So now here we can say that this is 3 over 4 kx minus kx is equal to W. Now, what about the work done by gravity? Because this is a conservative force, we know that the work done by gravity is equal to minus the variation of the gravitational potential energy. This is something that we have done in unit 3. Then that would be minus the final gravitational potential energy, which is UG at the position Y, minus UG at the position X. Now, the gravitational potential energy can be related to the kinetic energy, and this have been done previously, I think, in the previous class. So now let's do it again. Okay, I need some space. Let me do it here, then I will erase it. So we need to find what is the relation between the gravitational potential energy and the kinetic energy, so we can determine the ratio given by UG divided by K. Now, the gravitational potential energy for planetary systems given by minus G m divided by R, and the kinetic energy is given by half mv square. Now, V can be related to the central mass if we're talking about perfectly orbital circular periods. So that would be G m over R divided by half m. So the square root of G central mass divided by R to the power of 2. This cancels with this. Mass cancels with mass. Central mass cancels with central mass. G with G. R with R. That would be minus 1 over half, which is basically minus 2, which means that UG equals minus 2 the kinetic energy. Then this can be written as minus the double of kinetic energy at position Y, minus with minus that would be plus the double of the kinetic energy at X, again that would be, so the double of kinetic energy at Y minus the double of kinetic energy at X. Okay, so this is the work done by gravity. The double of kinetic energy by Y minus the double of kinetic energy of X. Now it's left just to convert this to be Kx, and that would be by 3 over 4. So 3 over 4 Kx minus Kx equals to the work that we're interested in calculating, plus the double of 3 over 4 Kx minus the double of Kx, and let me make some space here. And let me move these to the other side. That would be 3 over 4. I'm factoring out Kx minus 1. Now 2 times 3 over 4 is 3 over 2, taking it to the other side, that would be minus 3 over 2. Minus 2 taking it to the other side, that would be plus 2, equals to W. Now if you compute these fractions, they would be perfectly equal to 1 over 4. Then the work done by the force according to the work energy theorem is given by 1 over 4. So here we have Kx, making D to be the correct answer. Now exercise 11. If a person goes to the bottom of a deep mine shaft on a planet of uniform density, which of the following is true? Now remember, if we plot Fg versus R, if this is the radius of the planet, now here it will be hyperbolic, and from the center to the surface of the planet it is linear, and we have investigated this in class 2. So this is how the gravitational pull varies with respect to the position R. This regime or region corresponds to the inside of the planet, and this is outside the planet. And we need to see how does the person's weight varies with respect to R. So A, the person's weight is exactly the same at the surface. Now we know that there is a variation. The person's weight is greater than at the surface. So we know that this is not true because it is the greatest at the surface. It starts to decrease when we go to the center. The person's weight is less than at the surface, so this is potentially correct. The person's weight may increase or decrease depending on the density of the planet. No, that's wrong, especially that the density is uniform. The gravitational force on the person changes in direction but not in magnitude. No, it's gonna change in magnitude and the direction will remain the same, which is toward the center, making C to be the correct answer. Now finally, exercise 12. As an exit ticket for today's video, 2 satellites of masses M1 and M2 orbit a planet of central mass in circular orbits. The satellites travel in opposite directions with the speeds v1 and v2 as shown in the figure above. Their orbital radii are r1 and r2 respectively. Assume that central mass is much greater than m2 and m1. If u1 is the potential energy of the planet satellite system containing the satellite of mass m1 and u2 is 4 m2, which of the following expressions best represents the ratio u1 over u2? Now u1 is the gravitational potential energy between the planet satellite system. Now let me state something very important. There exists a gravitational potential energy between m1 and m, between m1 and m2, and between m2 and m. So you can consider different combinations. Here, because they're mentioning that U1 is for planet satellite, and we know that the potential energy is given by minus g coupled masses divided by separation distance. The coupled masses should refer to the masses of the planet and the satellite. So what is U1? U1 is minus g divided by the separation distance of M1, which is basically R1, and the coupled masses, which is basically M1 and the central mass. U2 is minus g, so this is central mass, M2, M over R2. And we need to determine the ratios U1 over U2. So U1 over U2 equals, now the minus signs would cancel, g would cancel, the central masses would cancel, and we would have M1 over R1 divided by M2 over R2, which is basically M1 R2 over M2 R1, making, if you look carefully, making C to be the correct answer. And that's it for me in this video, guys. See you soon in a new one.